Hello and welcome to today's video. In this video we are going to take a look at an example for the application of Green's theorem. So this video is called Green's Theorem Examples. We are going to consider two examples, and we'll start with the following. Let's say we have a vector field V of x1, x2 given as minus x2 and x1. Let's say we are considering a domain B that is defined as all x1, x2 in R2 with the property x1 squared plus x2 squared is less or equal to 1 and x2 is greater or equal to 0. This domain is something that you should already know, should be familiar. Let's have a look at a quick sketch here. So x2 is greater or equal to 0. That means I only draw the upper half of the coordinate system. And otherwise, this inequality here has to hold, and that obviously means that the length, the norm of x1 and x2, so the norm of x squared, is less or equal to 1. Or in other words, the point x lies within the unit disk. So what we have here is a disk of radius 1 around the origin, and in particular we're considering the upper half of that disk. So that is B. And the boundary of B is obviously this part here and this curve. So that consists of two parts that we want to parameterize. And remember, for the application of Green's theorem, we want to make sure that the domain that we're interested in lies to the left of its boundary. So we want to parameterize the boundary in a way such that this is true. And that means, of course, we need to choose the right direction for the parameterization. So if you want to parameterize this part here, then we will parameterize that in a way that the movement along this curve is in this direction here. So left of that curve would then be this area here. That is obviously where B is. And for that circular part here, we want to parameterize in a way that this circular part is oriented in this way here. So that left of that curve is down here, and that is where B is. Okay, so for this parameterization, let's call that lower curve here gamma 1, and that upper curve, let's call it gamma 2. Okay, so we want to parameterize the border, the boundary of B. And we do this through a closed curve that consists of two parts, and each of those parts will be a differentiable curve. So, closed curve, we call it gamma. That consists of two parts, gamma 1 and gamma 2. And each of those is differentiable. Now let's try to come up with a parameterization for that. Shouldn't be that hard. So for gamma 1, that's just a straight line, so that's kind of easy to parameterize. The x2 coordinate is always 0, the x1 varies from -1 to 1, so probably the easiest parameterization that we can come up with is this. We take -1 to 1 as the parameter interval, map to R2, and we simply say gamma 1 of t is equal to t and 0. And that corresponds exactly to this curve here. And for gamma 2, that's part of the unit circle. That's also something that you should know very well. We're starting here at this point, 1, 0, and then we're moving in counterclockwise direction for a total of, well, the starting angle corresponds to 0. This is pi over 2, so this is pi. Last point corresponds to an angle of pi. So the parameter space is from 0 to pi. And gamma 2 of t is simply given as cosine of t and sine of t. And as we said, please note that b is to the left of gamma 1 and gamma 2 in this specific parameterization. Now we want to apply Green's theorem here. And remember Green's theorem. Let's once again state the formula. Remember Green's theorem connects volume integrals and integrals of vector fields over curves. And the formula here is the integral over a vector field ds over the boundary of some compact region B, compact and simply connected region B, is the same as the following volume integral, so the integral over B itself of, well, V2, the second coordinate of our vector field, differentiated with respect to x1, minus V1 differentiated with respect to x2. And we integrate dx1 x2. And I want to apply that. Remember the vector field that we have here is this minus x2 and x1. Maybe let's copy that. Okay, so this is our vector field here. And that means if we want to compute this expression here, dv2 dx1 of x minus dv1 dx2 of x, well, what is that? Let's see, v2 is x1. Differentiating that with respect to x1 yields a 1. v1 is equal to minus x2, and differentiating that with respect to x2 yields a minus 1. So we have minus 1. And that means we get a total of 2 here, right? Okay, so what we get is obviously this part here of Green's theorem. That's integrating over 2. So the integral over b dv2 dx1 minus dv1 dx2 dx1 x2 is the same thing as the integral over 2 dx1 x2. Well, obviously this is 2 times the integral over 1, and remember the integral over 1 is simply the volume of the domain B. So this is equal to 2 times the volume of the domain B. Right, now let's see what we can say about the other side of this expression here. Well, we have already come up with a parameterization, so we can compute this integral directly as well. And what does that mean? Well, that means 2 times this volume here of B is, by Green's theorem, the same thing as the integral over V ds over the border boundary of B. And that is the same thing as the integral over V ds over gamma 1 plus the integral over V ds over gamma 2. Now, by definition of the integral of a vector field along a curve, let's see, for gamma 1, remember we parameterized gamma 1 from -1 to +1. That's this one here, and that is the formula, T0. So this would go from -1 to 1. For the integral, we need to compute the scalar product of V at gamma with gamma dot. So we need the scalar product of V of gamma 1 of t and gamma dot of t dt. That's going to be the first integral. Again, gamma 1 was given as t0, so gamma dot is obviously 1, 0. And the second integral, let's have a look at gamma 2 here. So that was, the parameter was from 0 to pi, and this here was the formula, cosine t sine t. So we're getting an integral from 0 to pi over the scalar product of v of gamma 2 of t and gamma 2 dot of t dt. And remember, gamma 2 is cosine t sine t. So gamma 2 dot is going to be minus sine t and cosine t. So let's do this computation here. So what we get here in the first integral is the scalar product of, well, v of t0. Remember, v is this vector field here, minus x2 and x1. So we substitute t0 into that field. What we get is minus 0 in t. And then we have gamma dot, that's 1, 0. And for the second integral, so we have cosine and sine. Again, we switch that with v and add a minus to the first coordinate, so we get minus sine t and cosine t. And we need to take the scalar product of this and gamma 2 dot, that's minus sine t and cosine t. So incidentally, the very same vector, dt. Right, so what do we get? Well, the first integral, obviously this scalar product is 0 times 1 plus t times 0, so that's simply 0 dt. It's It's going to be easy. The second one, from 0 to pi, we get here is negative sign times negative sign, that's sine squared. Plus cosine times cosine, that's cosine squared. And you can see that this expression here is, of course, equal to 1. So in total we have 0 plus the integral from 0 to pi over 1 dt. That's surprisingly easy. This integral, of course, is simply t. So we get boundaries 0 and pi. We get a value of pi. So that means we have now shown that the volume of B, or 2 times the volume of B, is equal to pi. That means the volume of B is equal to pi over 2. And you will hopefully agree that this looks reasonable. Remember, B was half of the unit disk. The area of a disk is given as radius squared times pi. The radius is 1 here, so the area of the unit disk is pi, and the area of half the unit disk, exactly the volume of B, is pi over 2. Okay, that was our first example. Let's take a look at something a little more challenging for the second example, part B. Let's say we have a vector field V given as V of x1, x2 is minus x2 to the power of 3, and x1 times x2 to the power of 2. And let's say B is given as the parallelotope with the following vertices: origin, so 0, 0, 1, 0, 1, 1, and 2, 1. So let's make a quick sketch. What does that look like here? So here's the point 0, 0, the origin. Then the point 1, 0 will be here. The point 1, 1 will be here. And the point 2, 1 will be here. So that parallelotope that we have to consider looks like this. So this here, this is B. And again, we want to parameterize the boundary of B. We want to parameterize that in a way such that the domain B is to the left of that parameterization. So we want to traverse this boundary in this way, then we go back and down, like that here. Right? So that is the boundary of B. Oriented such that the set B itself is to the left, or the interior of B is to the left of that area. All right. So you will note that, of course, we can easily describe B as a normal domain. In particular, we could say B consists of all x1, x2 in R2 with the following properties. Well, x1 which one is this direction here? x2 is this direction. So I suggest we bound x2 because we have this and this straight line here directly parallel to the x1 axis. So x2 is obviously bounded by those two, by 0 and by 1. Right, so that is the coordinate that is bounded by a constant. x2 is between 0 and 1. And then what about x1 as a function of x2? Well, as you can see, this line here going through 0, 0 and 1, 1, that is simply the line that corresponds to the equation x2 equals x1. Right, so that here is x2 equals x1. And this line here, that corresponds to the equation x2 equals x1 minus 1. Yeah, if you think of that, going further like this one, I will cross the x2 axis at minus 1. So these are the boundaries for x1, and that means x1 is greater or equal to x2, or x2 is less or equal to x1, and x1 is less or equal to x2 plus 1. Right? Solve this here for x1, we get x1 equals x2 plus 1. So that way we can describe B as a pretty simple normal domain. And again, please note that B is left of this boundary in the parameterization that we have chosen here. And of course we haven't made that explicit yet, right? So now if you wanted to compute the integral over the vector field VDS over the boundary of B, then we would have to come up with the parameterizations for those 4 parts. They're all straight lines, so it's not going to be that hard. But as B is a normal domain and a pretty simple one, it shouldn't be too hard to compute a volume integral of whatever function over B as well. So we're going to try that way first. And as you remember by Green's theorem, this integral over the vector field over the boundary of B is the same as the volume integral over B dv2 dx1 minus dv1 dx2 dx1 x2. So what we need to do is we need to compute this expression here for our vector field. And remember, the vector field was given as v of x1, x2 is minus x2 to the power of 3 and x1, x2 squared. So let's compute this expression here. And we have the integral over b. Let's see. We first need dv2 dx1. v2 is this expression here. And if we differentiate it with respect to x1, we get x2 squared. Right? So that is x2 squared. Then we have a minus. And then dv1 dx2. v1 is this expression, and differentiating that with respect to x2 yields minus 3x2 squared. So that's minus 3x2 squared dx1 x2. And well, you hopefully agree this doesn't sound too intimidating. Integral over b. Let's simplify that a little. So we get x2 squared plus 3x2 squared. Well, that's 4x2 squared dx1 x2. Okay, and now we just need to use our description of b. Maybe we just copy that down. So remember that was our description of B as a normal domain. So we can write that integral here as, let's take out the 4 to make it even simpler, 4, and then we have a double integral. The x2 is going to be the outer integral because that is bounded by constants. So the outer integral is x2 from 0 to 1. And the inner integral is x1 from x2 to x2 plus 1. And again, the expression here is 4x2 squared. We've taken out the 4 already, so that means an x2 squared inside remains. And we integrate dx1 first and then dx2. All right, almost done. So that's 4. We just copy this outer integral. The inner one, dx1, we integrate that. We get x2 squared x1 for x1 from x2 to x2 plus 1. So, simplifying that a little, that's 4 outer integral x2 from 0 to 1. Well, we need to substitute the bound, so the upper bound here, that's x2 squared times x2 plus 1. And the lower bound is x2 squared times x2. dx2. So as you can see, here we get x2 to the power of 3. Here we get x2 to the power of 3, so there's a minus here, so that cancels out completely. And we're left with only x2 squared times 1. Right, so that's just x2 squared dx2. Oh, sorry, that's a 2, of course. Okay, almost done. Let's integrate that. x2 squared integrated is x2 to the power of 3 over 3. Boundaries from 0 to 1. So what we get here is 4 times, well, upper bound is 1, so it's 1/3. Lower bound is 0, so minus 0. So that yields a value of 4 over 3. And you hopefully agree that was pretty simple to compute. Considering that the alternative would have been to parameterize those 4 edges here and then compute the integrals over the vector fields using scalar products and also using the differentials, the derivatives of those curves here. Also could have been done, but I would argue that this way here is the faster and the simpler one. So this concludes our little video on examples on Green's formula. And that also concludes this part of the lecture. So this is the last lesson about integration in this lecture. And as usual, of course, there'll be more examples in the exercise classes. And as usual, I hope I'll see you then.